of 61B. So today we're talking about graph traversals, and in particular we are going to start by doing the very end of last lecture because I augmented the visualization that we did towards the end to make it more clear what was going on. So first I want to drive home this really important point, which was given a graph. If we want to answer questions about that graph, this is a very common pattern where we create a class that we hand the graph to, and that class will carefully consider everything about this graph and figure out the information that it cares about, and then we can query this object for the answers. And those answers will generally come pretty quickly, and all the work actually gets done in the constructor. And so we saw an example of this, so I said, okay, imagine creating a paths object. You say, hey, paths object, here's a graph. Tell me everything about this graph with respect to vertex 0, okay, or compute everything you might care about. And then I can ask questions like, was there a way to get to 3 in that graph? And it will immediately return true, because she has carefully considered all the variables. Okay? And so the particular implementation we talked about in some detail at the end of last lecture was, well, we can imagine creating a marked array, which captures the notion of vertex marking that we did with our intuitive picture. And we have an edge2 array, which tracks how we got somewhere, which is useful for this path2 method. And so now let's do the same exact demo we did before, but now with some little purple circles that I think will make it more clear what's going on. Okay, so this is basically how the constructor for that paths object works. We give it a graph, and it starts by having all false variables, and edge2 is just some dummy value we don't care about. So I'm just showing it as a dash. So we're going to imagine that constructor has a helper method called DFS, which stands for depth first search, and I'll tell you more about that in a bit. And as I run this demo, I'm also going to show you the order in which this recursive method is called up here, just to keep track. So the first DFS call is to 0, and so what will happen when we go to 0? What's the first step? Marking. And then for each unmarked adjacent vertex, in this case 1, we will set the edge2 for 1, and then call DFS on 1. So in other words, after calling DFS, the result is we mark as true, and we set the edge2 value to 0. This is the way we remember that the way to get to 1 is 0. Okay. At this point, we have called DFS 0, and now we're going to call DFS 1. Do we return from DFS 0 yet? No. Okay. So we continue along. At this point, we mark 1 and set the edge2 for 2. At this point, where are we going to go next? 2. Okay, so we go to 2, so we mark 2, and once we go to, we call DFS of 2, which marks 2, and then sets the edge2 of its neighbor 5. Okay. Now here's maybe a question that's a little trickier, which is the next DFS call is obviously going to be 5, as noted in this list. How many different edge2s are we going to set in this next slide, do you think? Okay, 3. Any other guesses? 1. Okay, so in this case it's 1. And that's just because of the for loop, you'll notice that the edge2 happens before the DFS call. Okay, so just a subtle point. And in this case, then what we end up getting is the way to get to 4 is via 5, but we're not going to set the edge2 for 6 and 8 yet. And that's just the implementation I have here. So those are my order of DFS calls. We keep going along, and at this point, you kind of know what the story is going to be, and I encourage you to look at this again later. But the next thing I think that happens that's actually interesting is when we get to 3. So when we call DFS of 3, we're not going to change anything other than marking 3, but we're not going to set any edge2 variables. So there's only a purple circle on the left, and at this point there's no more children, so we just return. And so the first return that we actually have is DFS of 3. Okay, so that's the first call to DFS that returns. What will happen when we get back up to DFS of 4? We'll also return, so I'm marking that down there to say that's the order in which we returned. We get back up to 5. We don't return yet. We keep crawling along. We get to 7. Okay, when we get to 7, we just mark true. This is the very last value we fill in when we get to 8. And we return, 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 return. Okay, any questions? All right, so that's our depth first paths algorithm that we saw last time. But now it had circles, and hopefully it was a little easier to see what was happening. And where did I lost my slides. There they are. Okay, so this algorithm, wow, the silence in the room is palpable. Okay, so depth first search, that DFS method, that is a general term that you're going to hear. And actually, who here has heard depth first search before? Okay, who's not heard depth first search before? Okay, some of you guys, but not. The majority has seen it somewhere, even if you don't know exactly what it is. And it's just a general term for any graph search algorithm where you go as deep into the graph as you can before you do any backtracking. And it's actually used for all kinds of different algorithms that are slightly different from each other. So for example, if we do DFS where you just go and never mark anything and you can get stuck in a loop, that's called DFS. The one where you add marks to avoid loops, that is also called depth first search. The version where you mark where you came from and your marked values, that is also called depth first search. And there were other algorithms like topological sort, which we'll talk about later in this lecture, also called depth first search. So just be aware, depth first search is a very blanket term, kind of like walking, right? Like there's a lot of different ways to walk, and that's that. So there's more than that. Okay. So this is what an implementation might look like. I have two variables that are for tracking all the information that we've observed. We have a marked array and an edge 2 array. And then we also have our start vertex that someone gives us. Okay? This DFS function is what does all the work, and this just basically does what we were doing out loud. It sets marked for each neighbor. We check to see if it's marked. If it's not marked, we set the edge to and DFS. Okay, so there you go. And as we said last time, the way that we would write the path2 method, as you may recall towards the very end of lecture, actually I'll just ask it again. So after I've run this constructor, how do I implement the hasPath2, say, 6 method? So there's another method in here not shown. It's called hasPath2. Yeah. Yeah, just whether or not it's marked. And that tells you whether or not there's a way to get from S to 6 or whatever. Okay, so the runtime of this algorithm is V plus E. It's very similar to that graph printing algorithm we spent a lot of time on last time. And the basic idea here is that each vertex is visited exactly once, and each edge is used exactly once as we do this. Okay, so each visit will cost us constant time, and the amount of space it takes is theta v. Because at deepest, your search will go v levels deep, and the call stack depth is going to be at most v. So if you're tracking, if you have to somehow remember where you came from somewhere implicitly, it'll take a little space. Okay, so the runtime, though, the reason it's v plus e is, again, look at the picture, and you can see that every vertex gets visited exactly once, and I guess I should say each edge is used exactly once. I'm not sure quite why that's not there. Okay. Now, I'm not going to belabor that point because it's very similar to something in a previous lecture, something I said was quite tricky. All right? So that's our first graph problem we've solved in exact detail. That's the ST paths problem, which is how to get from a source to some set of targets. Okay, any questions? Yeah. So the question was, how is this related to our tree traversals? And we're going to talk about that in a little more detail in a bit. So I'll table it for now, but it is very closely related to our tree traversals, yes. In fact, it is one of them. So could you do a general version of this where instead of providing S, we provide only the graph? Sure. And in that case, you maybe have a two-dimensional array of marked and edge 2s. And that would be pre-caching every problem you might care about. And nope, actually, I'm just going to cut it off there. That's the multiple source variant. All right. Oh, yes. If you have two neighbors to go to? Yeah, so if you have multiple neighbors, it's just going to be in whatever order g.adj returns. So it'll just be based on the adjacency list, and we'll see a visual example shortly. So to your question about how does this relate to tree traversals, very prescient question, by the way. I had slides ready for you. So just as there's many different tree traversals, pre-order, in-order, post-order, level order, there's lots of different graph traversals. And a graph, of course, is nothing more than a tree that allows cycles, right? Or a tree, you could say, is a graph without cycles. And so just as there's many tree traversals, there's lots of graph traversals. We can have, for example, the DFS pre-order, which is the order of DFS calls. We can have, and so we had on this graph, it's 0, 1, 2, 5, 4, 3, 6, 7, 8. How do we compute this? Well, we just run that demo we did before, so that's where that came from. There's DFS post order, which is the order in which we return. Anybody remember what the first one was that we returned from? 3. So 3 is the first one on this list. And there's also level order, which is an increasing distance from S. And this is like level order in a tree. And so in this case, it would be 0, then 1, then 2 and 4 are equally far from 0, and then 5 and 3 are equally far, and then 6 and 8, and then 7. And I've just put spaces there at the very bottom of the slide that hopefully you can see, but you'll get a chance to do it in a moment. That will allow you to, actually, can you not see it? Anybody out of curiosity? All right, yeah, you guys, well, it's okay, because I got one for you. Okay. So I'd like you, just using your intuition, even though you couldn't see the example, try and figure out which of the following is not a valid level order traversal from vertex 2. So as we spread out from 2, what's not a valid level order traversal? Okay. All right. So, looking at these, who seems to be the problem child? Let's see, B, 2, 3, 4, 7, 5, 6. And the problem in particular is the 4. So 4 should not come before 5. That's the issue. So B is our problem. Needs to be 2, 3, 5, 2, 3, 5, 4, 6, then 7. But anything that's on the same level, they can be permuted. All right, so that's the level order traversal. Pretty natural notion, I think. Any questions about this? All right. How about this one? Slightly different graph, and the question is, which of these are valid level order traversal? This time it's which are valid. Okay, and there may be more than one correct answer, maybe not. Give it a shot. Okay. All right. So in this case, we have one correct answer, and it's A. Now, the key point here is that there are two different ways to get to 4, but if we're doing a level order traversal, we say that this is distance 1. So if we were to imagine annotating with each vertex with its distance from the source, 2 is 0 from itself, 3, 5, and 4 are 1 away, and 7 and 6 are 2 away. Okay. Maybe that would be useful to annotate. Yeah. Mm-hmm. So if it's undirected, okay. So in an undirected graph, yes. In a directed graph, if you search from 5, 2 is not considered 1 away. Yep. Unless you define level order traversal going backwards on edges, which you could, I guess. Yeah. Two, 3, 4, 5, 6, 7. Yes, that would be fine. Yep. Yeah. Okay. Great. So that's level order traversal. All right, one more for you that'll bring us to our next problem, which is DFS post order. So this is the order in which you return from DFS. This is the thing we were doing before. So we're kind of going backwards in lecture for a moment, but it'll take us forwards to an interesting new problem. So if you're not quite sure where to start, try and figure out what the first DFS is that finishes, and we're starting at 0. Like so spooky how quiet it is. So in this particular case, I have given you the adjacency list, so there's only one right answer because of the way I'm describing it. Okay, so in this case, the correct answer is 74130, and the idea is the first one that finishes is 7. But more generally, if you imagine what DFS does, when it starts at 0, does it go to 1 or 3 first? 1. Why? Not because it's smaller, but because it's earlier in the adjacency list. So in this case, well, I guess they come in increasing order, so I guess it's also equivalent. So we go 1, 4, 7. 7's the first it finishes, then 4, then 1. 0 does not happen yet. 3 finishes, now 0 happens, or it returns. All right, any questions about this? And so this feels a lot like post order from trees. I think it is exactly the same, yeah. If you took a different path, is that what you said? Okay, let's say 3 pointed at, I don't know, 5. Well, no, I don't know, 6. How about that? So say 3 pointed at 6. Then what would happen? It would be 7, 4, 1, 6, 3, 0. Yeah. I'm going to put it back, though, so that anonymous hippo or whatever, anteater, is not confused. All right. It would be a shame if anteater was having a sad day. Never confuse an anteater. Okay, that's my suggestion. All right. Has anybody here seen an anteater in real life? I have never. How was it? Yeah. Was it eating ants, or was it just living its life? Just doing its thing. Okay. Yeah, that's my aspiration, I think, see an anteater. There's a petting zoo somewhere around here. I don't think they have an anteater, but how about anybody seen here a coati or a coatimundi? It's a coast. Oh, yeah. Where'd you see a coati? Oh, yeah, okay. Damn it! They're from Costa Rica, these things. Tell me, what's your question? It's the same thing, basically. Yeah, it's almost the exact same idea. That's a funny question. I haven't really thought about it in the last year, so I don't actually know. So the question is this the same thing as post order in a tree? It seems like surely it should be, is it? You guys are thinking harder than I am, yeah. Yeah. Yeah, so a graph is a generalization of a tree that allows cycles. But if you think about the way we phrased tree traversal, it was something like, post order is, you go to all your neighbors, and then you visit. Okay, yeah, so it's the same. Yeah. Okay, cool. All right. Now, the question I wanted you to ask is, why is this useful? But you didn't, so I'll tell you why it's useful. So I'm going to talk about an algorithm called topological sorting. And you could think of this as a question. It's kind of like, but not exactly like, you have prerequisites for classes where you have to take class 0 before 1 and 3 and so forth. And so you could think of each of these arrows as prerequisites that must happen. Maybe you could think of 2 as start the car, 3 is like press the gas pedal, 5 is like, consult the directions, or like have your navigator explain where you're going, 4 is get there, 7 is eat a meal, or whatever, right? I don't know. Anyway, so you have a set of tasks where the arrow tells you what must happen before another. And what I'd like you to do is figure out an algorithm that gives you a valid ordering of tasks. So let me give you an example of a valid ordering. I could do 0 first. Then I could do 2. Then I could do 1. Then I could do 3. Then 5. Then 4. Then 7. Then 6. And I would obey all the prerequisites, and I wouldn't get dropped because I didn't have the prerequisites. So think about it for, minute and a half. Just try and imagine how you might compute a valid ordering. And if you're not sure how to get an algorithm, at least think of where you might even start. This is worth 30 points. And it has to be done at once. All right. Very funny joke. It's not like we have a GPA cutoff in the future. I'm still stressed out about it, but not today, not right now. Wow. Dang. Okay, any thoughts on where we might start? Yeah. Yeah. Oh, does it know it's there? No, but you could build the reverse of the graph, I guess, technically. It's not necessary for this. There might be an algorithm that does that, though. Ooh, I know where you're going. All right. Any thoughts? Suggestions? Yeah. Okay, so the idea is I found a really powerful laser in this drawer. And it's not that powerful in this distance. Anyway, these two right here, this is fun. You don't have to have this thing appearing over and over. Anyway, I'm going to try this, see what it's like. So these two have the special property, nothing points at them. So it seems like a good place to start from and do what? Traverse, okay? And where do you end up? At like 7 and 6. So what do we notice about where you end up? They don't point anywhere. That's true. Okay, so it seems like starting up here in some way. Well, if we just get like the DFS order, let's see. Say we start at 0. If I just do the DFS pre-order of this thing, is that going to be useful to me? Is that a valid ordering if I just start at 0 and count them off? Not quite, because if I do 0, then I'm going to try and do 1 next, and then 3. Actually, does it work in this one? Yeah, if I do 0, then 3, that's no good. I've violated the constraint. So you can't just pre-order from 0 and 2. What else? Yeah. Yeah. Do DFS and then reverse it. What's it in this case? Post order. Okay, so if you do the post order, you'll notice something really interesting. The post order, the first to finish is 7. So it's like where you end up is where you want to be last. So this is the spoiler. You got the right idea, which is you do a DFS traversal from every vertex within degree 0, and then you record the post order in a list, and then you give the reverse of that list as your correct ordering. Now, there's one little tricky part that's hard to see in the middle of lecture, which is that it's not enough just to do the traversal from 0. You also need to traverse from every vertex that has n degree 0, and in that way, you will make sure to get the right answer. So you identify all the vertices that have n degree 0, do a post order from all of them, and you'll get there. So let me do a demo, and then I'll take the question, because I want to make it's much more clear after you've seen it, and I'm happy to take the question after. So I'm going to start just arbitrarily by DFS post ordering, or just DFS searching from 0. We start at 0. We go to, let's say, 1 next. We go to 4. We go to 7. Those are all marked. And the first thing we complete is 7, which is another way of saying 7 is something we should do much later because it's so far down the end of the prerequisite chain. We go back up to 4. 4 is now done, so it's fine to do in theory. Okay, so we get back up to 1. We get to 0. We're not done with that. So now where do we go? 3. Okay, we return from 3, and we're done with, at this point, 0. So we've done a post order, but it doesn't cover all of my constraints, right? So this is not an answer because it's in the wrong order, first of all, because I don't want to do 7 first, but also it doesn't take into account this other part of the tree that was not reachable from 0. So what we do is we look at all the remaining vertices of n degree 0. So we start at 2 again. 3's already marked, so we're not going to bother with that. We go to 5. We go to 6. Okay, 6 is done. 5 is done. Okay, that thing's there. And then 0 is done. And so we end up with the post-order traversal of the whole graph. Now, this post-order is a little different than the one I told you about earlier because this is like a post-order with restarts. And the one we were talking about before did not have restarts. So it's a very closely related idea. And unfortunately, the same terms are used for both restarts and no restarts. So if you ask somebody what DFS is, sometimes they'll assume you're talking about something with restarts. Sometimes they won't. But here we go. We got those restarts. And so in this case, a valid, but not the only valid, particular way of satisfying the prerequisites is 2, 5, 6, 0, 3, 1, 4, 7. Okay? Now, questions or other? Yeah. Yeah. How would you find all the vertices of n degree 0? Or are you suggesting a way to do it? Yeah. Oh, you asking how we would know where they were? Oh, yeah. I mean, imagine what you do is you collect them all, and you have them ready in a list ready to go, and then you'll call DFS on them. What's kind of interesting about this is you don't actually have to start with the vertices of n degree 0. You can actually start with any arbitrary vertices, but it's intuitive to understand more so why it works with n degree 0, but actually you can show that it works no matter where you start, as long as you just keep restarting until you've visited every vertex, yes. Okay, well, I guess first I should say why it's even called topological sort. So it's called a topological sort because, well, topology, it's like space. It's like the arrangement of things, right? And so the reason it's called topological sort is that once you get an ordering which obeys our constraints, you're sorting, say, left to right. So we take vertex 2 and we drag it over to the left. Then we have, so this is the thing we computed using this example, right? So we take this sequence of digits, and we use it to tell us how to order our vertices. So we drag 2 all the way to the left, we put 5 next to it, 6 next to it, 0, 3, then 1, then 4, then 7. Here they are. And you'll see that there's something very special about this diagram here, which is all the arrows are pointing rightwards. And so that's why it's called a topological sort. Now, the question is, why is this better than like selection sort or insertion sort or merge sort? It's actually a totally orthogonal concept. We're not actually doing sorting as you and I know it. It's called it's a topological sort as opposed to like a ordering sort or a value sort. Okay? And one of the key points here is that understanding the relationship between two different vertices is a little bit non-local. You can't just say, look at the bits in this box and the bits in this box and say which one's less. It's an emergent property of the whole graph. All right, any questions about this here? So if you're trying to figure out, like, how do I obey prerequisites, this is one approach. It's a pretty common one. And I think the more important thing here is not so much this exact algorithm. It's that a problem which seems to have very little to do with depth-first search is solvable, in this case, with depth-first search. And this is also true of a bunch of other problems. So I'll give you another. Actually, any questions about this before I give another one? Yeah. How is reverse post-order different from pre-order? This is a great question. So if you were to do, let's see if I can see it here. If we do just pre-order here, we get 2, 5, 6, then we'll get 3, 4, 7. So the 0 is not there. So if you only did the pre-order starting at 2, this 0 wouldn't pop up, as an example. So there's something special about the way we did the restart so that it feels a little different. Yeah. But the relationship between the reverse post-order and the pre-order, or there's also another interesting question, which is even a little trickier, which is, what's the difference between, I think it's the pre-order of the reverse graph and the reversed post-order? That's another one that I think is a little challenging, but I shouldn't have even said that out loud. All right, yeah. What else we got? No, the pre-order is not the same if we start at 2, because the pre-order, it won't have a 0 before this 3. The post-order, remember that the difference is we did the post-order with restarts, and then reverse the result of all of that. Well, if you do the pre-order with restarts, 3 will still occur before 0, because it's going to chase your way all the way down. Yeah, so pre-order, you can't do it. Yeah. This topological sort, does it work for all graphs? Good question. Does topological sort work for all graphs? All directed graphs. Okay, it's a good point. Doesn't work for undirected graphs. Yeah. If you have cycles, then you're going to run into trouble. But that's not such a surprise because it's supposed to be about prerequisites. So if like one of the prerequisites of 61B is you have to take 61A, and one of the prerequisites of 61A is you have to take 61B, there's no way to solve it, obviously, right? Okay. All right. So there's a whole universe of other graph problems you might have, like given a map of countries, can you find a way to color them in such a way that, let's say, you only use 2 colors, red and black, let's say, and you want to just traverse the world's map and try and figure out, is the world amenable to having red-black colorings of countries such that no 2 countries share colors? You could do that with a graph traversal. Countries is probably not a very interesting one because clearly that won't work, but other kind of graphs, it could be less obvious. Okay, if you want to know what this looks like in code, again, I don't care that you look at all the little details here. This is just the textbook implementation. I'm showing you to convince you that there's nothing magic. Okay, so the key points is we create a stack of integers, which is going to be the reverse post order. whenever you create a public one of these depth first order objects, it's like a magic device. Why is the formatting all gross? Hold on a second. We can't stand this. This is not good. We have to fix it. I'll get very upset. I am the style checker today. What happened? Why are we in the depth first demo? Who killed my thing? Meh. Okay. It's spring break, though, so. Nope, I opened the wrong thing. What's this lecture about? Graph traversals. All right. You're like, I'm out of here. This sucks. Hold on. That's the 2017 version. All right. Did someone delete it? It was this powerful laser. I shouldn't have dared use this on my slides. Okay. There we go. We're back. Back in business. All right, got a question. Has anybody done this terrifying thing where you scuba dive in a cave before? No, I never have either. But here it's like really awesome and really scary. Okay. Yeah. All right. Nope, we're ahead of ourselves. Okay, let's fix the formatting. Who is it? Yeah, I'll take it if you want. It's the day before spring break. There's no rules anymore. All right. Okay. Close enough. No rules. Don't have the spacing line up. I'm happy. So when you create one of these objects, you create a stack, and you create a marked array that has as many booleans as there are vertices. Then for each vertex, if it's not marked, we call it DFS. And in this case, the special point is that whenever we go through each of our neighbors, after we have gone through all of them, we'll push to the stack. Now, it's not obvious just staring at that we have magically done what we described out loud. But in case you're curious, how would you implement it? It looks like that. In this case, we return an iterable, which in this case is the optional textbook version of a stack. And so when you iterate through it, you get the answer back in the reverse order that you put stuff in. Now, for those of you guys who are like serious Java, the real heads as they put it, like people that are just really into the language, the Java util stack will not work if you do this because the iterator works backwards. Okay, anyway, that's that thing. So what we've got here is a topological sort. It's a totally different problem than the ST paths problem, but it is also solved using depth first search. And in this case, it's just a slight tweak. The difference is we're storing some stuff in a stack, and we get a different answer. And graph problems have that feeling to them. So it makes extremely good, insanely difficult exam problems, because look at that. You add a stack, and now you suddenly solve a totally different problem. Pretty exciting stuff. All right. Moving on. Yeah, sorry. I was too busy ranting. Okay, yeah. Theta v space. The way you prove it is the two places that space get used are the stack and also the call stack depth. And the depth of that call stack is never going to be deeper than v. And the stack will also never be more than v. Yeah. The call stack is basically just the sequence of DFS calls. So the computer actually has to somehow remember how to go back up once you've finished a DFS call, where to return to. And in 61C, you'll learn exactly how that works, if you take it. Okay. All right. One more, breadth first search. All right. This is depth first search's cousin, and it is a pretty intuitive idea, and it also happens to be level order. So when I said level order on a graph, that's the last time you'll ever hear me or anybody else ever say that, unless you come back to watch lecture again next semester, I guess, or in the spring. Level order in the real world is often called the order visited by breadth first search, and what it ultimately, that's what it does. Okay, yeah. So how do we find the level order? Well, for trees, we had an algorithm called iterative deepening, and we saw that it was a bad algorithm for long, spindly trees. It was theta n squared. It was a hard analysis problem. And so now what we're going to talk about is an alternate variant of this same idea called breadth first search that has two advantages. One, it works well on graphs and not just trees. And secondly, it's going to be guaranteed linear time as opposed to being quadratic in the number of nodes or vertices. And so the idea is that, and this is a very different feel, is it's not recursive. Okay? What we're going to do is create a queue, just like the idea of a queue, the opposite of a stack. You know, you put stuff in, it's a line, things come out in the order that they went in. And we're going to start it off with the starting vertex, and we're going to mark that vertex. And this queue we're going to call the fringe. Now the word fringe, you are going to see this a lot in 61B. If you go and take an AI course, like say 188, you're going to see the word fringe all over the place. You'll probably also see it in 170. And fringe refers to like the edge, right? So curtains, they have a fringe. Here, I'll get you a fringe to look at, right? This is the fringe right here. Okay, it's like the end of the thing. That's where you're exploring, okay? Now, the reason that we call it the fringe, it's because that's the frontier where we want to go. Okay. And so what we're going to do is repeat until the fringe is empty. The following process: we're going to remove the best thing from the fringe. In this case, it's going to be the oldest thing, and then we're going to add to the fringe any unmarked vertices adjacent to whatever we just pulled out and mark those as well. And here's how it goes. Okay. So the Q is going to represent all the things we're thinking about doing in the future. All right. So we're going to start by initializing the fringe, which is a Q, which currently has nothing in it. And now we're going to add the starting vertex S. There it is, and we'll mark that vertex. Oh, one little thing. So Google Slides is messing with me because this S. Can we show you? Jeez, it was worth it. Okay, look at that S. See where it is? Okay. Now the problem was I didn't actually make this box big enough, so it's like a rendering error. So just in case you ever have that happen, this last S, when we get to the last slide, it'll work fine. But these early S's, that one's going to be good. But this one's going to be ugly, okay? So anyway, just in case you ever have that happen to you, that's why it happens. I just figured that out pretty recently. Didn't fix it on these slides. Okay, Google Slides lesson aside, let's go back to 61B content. So we take S, we put it in the fringe, and it moves up just a little for fun because of Google Slides, and now it's marked, okay? We do not set edge to. So this is the whole world that we're thinking about exploring. So we'll take 0 out of the queue, and then we'll consider each of its neighbors. So right now, V is the active vertex. And so what are V's neighbors? Only 1. So we add 1 to the queue. We mark it, and we set its edge to. So anytime we find a neighbor that is unmarked, then we do these 3 steps to it. Okay? So now we have edge to is 0, marked is true, and we continue along. So we take 1 out, and in this case, how many neighbors does 1 have? 2 of them. So we're going to say 2 and 4, you should both go on the queue. So hopefully it makes intuitive sense that if we're trying to travel outwards from the source, we need to make sure that we have them all together waiting in the fringe, ready to get processed. So 2 and 4 go in. Okay? So we can already smell a little bit of an invariant. You might imagine the invariant is the queue is all of the things that are equally far away from the old boss or something like that. That's not quite true, but it's close to true. And in this case, we'll set these to be marked, and we'll set their edge to. Now, we'll notice that we've marked them before we've ever really visited them, and there's these little subtle implementation details. You can imagine trying to write this code and actually not marking until you actually dequeue it, and that'll be a slightly different algorithm. But, yeah, so it's some little subtleties. Okay? Okay, so at this point, we have now marked 2 and 4, and we've set the edge 2s to be 1 for those vertices, saying that that's the best way to get there. Okay? Now, it's really important that we set these edge 2s now, and not later. Like, why don't we just leave these empty until we actually dequeue them? Just give me a rough, intuitive picture. Any ideas? Yeah. Well, it's not so much necessarily we'll be able to find our way back, because we're not going to call... Because we don't care about coming back to 1, actually. After we've done 1, we're done with it. Say again? Save time? It's not quite that either. Nope. Okay, this is fun. Yeah. Yeah, it wouldn't necessarily be the right distance. So let's suppose we wait to actually do these until later. It's possible that in the course of this algorithm, we're going to get to 4 again. And then, like, you can imagine, depending on how you do things, you might accidentally set the path to be something longer. But as soon as you see a vertex, right, I'm spreading out like a disease across the graph. As soon as I see someone, I want to mark you are going to get, the way to get to you is through me. Because I am, like you can think about the invariant as, this is the fastest way to get to 1. We came from 0. So there's no reason not to set these right now, because they are adjacent to me. I am the very best incarnation of 1. And maybe at some other point, the graph might have some structure, you get back to me, but you guys should have already been marked with this distance. Okay? So it's a subtle little point, but an important one. Okay, so now we have 2 and 4 in our queue. And now we're going to take something off of the queue, and it doesn't actually matter what order these are put into the queue. But in this case, I'm saying 2 went first, then 4. So we take 2 out next. So 2 is now the active vertex. And so if we look at its neighbors, we have 1, we have 5. Do we do anything with 1? No, it's marked, because this is for each unmarked neighbor of V. Now imagine that we didn't have that rule. Imagine that we actually went and set the edge 2 to 1 is 2. That would be bad, right? We're saying the way to get to 1 is to come from 2, but no. You've just overwritten a better path, which was from 0. And in this case, best means correct, because this whole algorithm is supposed to be doing a level-ordered traversal, a breadth-first traversal. However, 5, the best way to get to 5 is guaranteed through 2. How do I know? Here's the question. How do I know that there isn't some other path, maybe, from 4 that gets to 5 even faster? This is a hard question. I mean, it's hard to answer because you can see the graph in front of you. You're like, it's not. But so here's 1. We went to 2. We're going to say that the best way to get to 5 is through me, not through whatever my siblings might have in mind. Yeah. Yes. So if 4, my brother, was so good at getting places, well, he would have been in the queue first. That's the answer. Okay? That's an important point. So you're relying on the fact that you are the best and that everybody in the queue is worse than you. Okay? And then it's a result of knowing that fact, you're willing to demand or state that all the things that you see should go through you. Okay? You're the decider. All right. That's a George Bush reference, by the way. All right. Now we got John Bolton back, so good. Okay, so coming up on 5. So 5 here, we will now mark 5 and set its edge 2 to 2, and we'll add 5 to the queue. So in this case, who should come off the queue next, 4 or 5? Just intuitively. Like, what would be the better branch to explore next? 4, and that makes sense, because 4 is actually your uncle, right? Or your, what is this? This is a confusing relationship. This is your mom, grandparent, uncle. Wait, I'm confused. What is this? Uncle. Okay, it's your uncle. So, yeah, uncle goes first. Thank you. I have a confusing life because I have a couple of nephews who are 3 years younger than me. So I've always been confused, especially about cousins, uncles, nephews. I don't know what's going on anymore with my familial life. Everybody's a different age. Anybody else have nephews that are almost their age or nieces? What's up? Cool. Wait, does anybody have nephews or nieces that are older than you? Oh, yeah. Cool. You guys are way cooler than me. Jeez. How much older? Who's the contest? 30? Okay, that's a lot older than you. Assuming. Anybody have a 10 or 12-year older nephew or niece? How much? All right. Congratulations. All right, good. So anyway, our queue has 5 in it now, and we've matched. So actually, we've just taken 4 off. What are we going to do next? So try and predict what circles will appear in this graph. Okay, it'll be the 3 row. So we set 3's edge 2 to 4, and we set mark to true. So we'll continue this process. You can watch this V hop around. I'm not going to go through it in a lot of detail here, but that's the whole sequence. One thing I do want to notice that, again, I encourage you to look at this whenever you're on airplanes to go wherever you're going or taking BART to Warm Springs. So whenever you watch this demo go, you'll see that V hops around, right? It doesn't move locally. Look, 5 to 3, and that's because the queue is not local. And so that's breadth first search. All right. Me? Okay. I heard the number 36, which is my magic number, because that's so old. All right. All right. Breadth first paths. This is what the algorithm looks like. Actually, any questions about the conceptual idea? I took away the picture. All right. So here's what the breadth first paths implementation looks like. You have a marked array, an edge 2 array. You will write code that looks a lot like this, especially in Project 3. So don't worry. You'll like it. It's cool. You'll build Google Maps, basically. So anyway, we will build a queue. We in-queue the start vertex. We set it to true. As long as the queue is not empty or the fringe is not empty, we take the best thing out for each of its neighbor. If it's not marked, we in-queue it, mark it, and set its edge to, just like we've been doing. Okay? So not such a big deal. So why does this work? I've alluded to it as we went, but the basic idea is that the fringe, in this particular case, it always consists of the following. This is the invariant. This is how you can prove that it works. It has all of the vertices that are distance k from S, and all the vertices that are distance k plus 1 from S, and nothing else. And this set might not be empty. This set might be empty. You might only have k from S. Okay? But it's never going to be anything other than those two things, and these will always come before these, right? So distance k is better than k plus 1. And this is really handy as it happens for finding the shortest paths. This takes v plus e time, again, because each vertex gets in-queued exactly once, and each of its edges gets used exactly once. And it uses v space in the worst case. So I could be big O-ing these. But it uses v space in the worst case because it might need to in-queue all of the vertices if you have a graph with a vertex that points at everybody else. Important point is that no vertex gets enqueued more than once, so there's no chance that this goes quadratic or exponential or anything. Okay? So question for you. Would this be a good algorithm for navigation tools like Google Maps? I'll let you think about that. Assume the vertices are intersections and the edges are roads that connect those intersections. So it does a level order. It feels like it should be good in the sense that it goes outwards. It doesn't drive you to Boston before you get to Fremont. All right, what do you think? Good? Bad? Anybody see any problems? Yeah. You guys will have to figure it out. Some roads are longer than others. So it's good. No, bad? What does that mean? Bad, right? You don't want to minimize the number of intersections. You want to minimize driving time. Because, of course, if you wanted to get on I-80, you can actually drive all the way across the country, and that's only like 3 intersections. Okay? It can also be used, for example, there's this notion of people are only separated so many degrees. You can use breadth first search to do the Kevin Bacon game, the 6 degrees of Kevin Bacon, where here's Kevin. This is from the optional textbook. This is not mine. So Kevin Bacon was in the movie Animal House, which had Donald Sutherland in it. He was in a movie called An American Haunting, which gets you to Vermin Dobchev, who I've never heard of. And in this way, you can figure out how far apart Kevin Bacon is from any given movie or actor. Okay, handy. All right. I guess we got 3 minutes left. Anybody got any questions about anything? Yeah. My plans for spring break are answering email, cleaning, figuring out what to do about that problem that people are upset about, and then just generally working on maybe. I mean, it's fair. I don't know. I got to get information. We're going to finish grading it, see how many people misinterpret it. Fair point. But yeah, working. But working without new things arriving to crush me. Yeah. Yeah, in terms of studying, what I think priorities would be, I think that doing all the B-level problems from everything is my first priority. Finding a group of people, if you don't have someone that you get along with well, you can argue with, and trying to meet like in an ideal world, you would every day or every other day meet up for like a half hour, talk about problems occasionally. So that's what I would do if I was you. It's kind of hard, tall order. What else? Yeah. Coolest application for graph traversals. That's a hard one. I don't know. How many really, really cool ones? I mean, the ones that involve if I think of a math perspective, the ones that involve trying to prove that graphs are isomorphic are pretty nuts. I don't know. They're really interesting. Yeah. I know. Seam carving. That's homework 5. Yeah. Things you should learn or do over spring break that are cool. It depends on your life right now. So if you're in a position where you're struggling academically, I think you should focus on getting caught up there. You're here on the last day for spring break, so probably a little less true than average people. I think exploring your humanity, which has been somewhat suppressed by the fact that you're at a high-pressure school, that sounds good. I mean, that's fine. That's fine. You're trying to learn how to, lead the world, and that means you have to give up a little of yourself. So maybe it's a good week to get a little back of yourself. I don't know. Go to the beach or something. Yeah. Have some fun. Yeah. A favorite graph? I don't know. Do I? Probably. The graph I made for the midterm in spring 2015 when we had 4 different finals where we had an answer that was easily explained to someone else. So you could be like, oh, the depth first traversal was potato. But then we had it secretly changed on each exam because they were at different times. So that if you put down the word potato on exam 2, we knew you had cheated. That was my favorite graph because it was really, really intricate to build so that it was indetectable. So anyway, that one was fun. Yeah. 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 Sure. Yeah, I got one more question. Yeah. Mac or PC? I actually prefer PCs in general. The one thing I like about Macs is the trackpad. That's it. So if you can get me a trackpad that works on a Windows computer, or even better, a Linux laptop, my God, please, save me. All right. All right, thank you, everybody. Enjoy your spring break, or don't. All right. Yeah, I'll be up here for a sec. Yeah.